Hi, I'm Jeanne Johns, and welcome to Risk Matters, where we share our experiences in high-hazard industries with the ultimate goal of eliminating industrial accidents and keeping people safe. Today, we'll be talking about a real-world example of how the decisions made during the project conception and design phases impact future operability and ultimately the ability to effectively operate and manage risk. To dive further into this topic, I'd like to introduce my guest, Paul Eagar. Paul worked for me during my time as CEO of Dyno Nobel, joining Dyno from the South African chemicals company AECI, and more specifically the subsidiary AEL Mining, which specializes in supplying civil explosives and servicing the mining industry. While at Dyno, Paul oversaw all of our operating plants in the Americas, which included 4 major process plants and 6 discrete manufacturing assembly facilities. Later, we'll be diving deeper into one of these plants, a greenfield world-scale ammonia plant on the U.S. Gulf Coast. But first, I'd like to welcome Paul to today's podcast.
Thanks, Jeanne. It's a pleasure talking with you today.
Paul, I'd like to start today by going back to the earlier days of your career with AEL. And as regular listeners will know, we've spoken about how to manage operating risk in a number of different high-hazard industries. And one important underlying aspect of doing so is the operating capability and excellence. In many ways, a reliable plant is a safe plant. So given this, Paul, can you share with me a little bit about your operating philosophy? How and where did you learn what good looks like in operations?
The various companies which I've worked for each contributed in a unique way to my view of what good looks like. At AECI in South Africa, there was a strong focus on the development of people at both leadership and operational levels. There had not been many opportunities created for the vast majority of the population when it came to primary, secondary, and tertiary education, with the result that there was a far greater onus on companies to develop talent required. It was here where I learned the value of well-structured training programs at both operational and leadership levels, as well as the impact that coaches and mentors can have on one's career. Ensuring that people had the means and ability to perform their jobs effectively and creating a strong sense of accountability was our shared leadership philosophy. As we all know, committed and competent people are the backbone of safe, reliable operations. I also learned the value of having well thought out manufacturing standards, which deal with aspects such as process safety, operating procedures, engineering, and plant reliability. Establishing communities of practice with subject matter experts, keeping these standards and best practices current, provides learning opportunities across the organization. Ultimately, the various operating metrics will indicate whether we have reached good, but the focus should really be on all the contributing factors leading to greatness.
Paul, it's an interesting point you make about formal training programs, something that I think we often underbake in favor of the easier learn-it-on-the-job approach. As you mentioned, the particular circumstances you encountered in South Africa, where structured training was required for a company's success, enabled to see what good or even great looks like in this aspect. And as many of the high-hazard industries are now going through a demographic change-out, I believe that formal training will need to take a larger and larger role going forward. I'd now like to move on to your time with Dyno Nobel. What did you observe when you joined us, and how did you determine your priorities across our diverse portfolio of assets?
Yeah, as you say, Dyno Nobel has a vast array of manufacturing operations. On the chemical production side, there were assets ranging from modern, world-scale ammonia plants to 60-year-old nitrogen facilities, as well as PETN plants used for the production of high explosives, which are those chemicals which detonate with reaction rates of about 20 times the speed of sound. On the other hand, Dyno's discrete manufacturing plants range from fully automated, high-speed assembly facilities to 100-year-old plants of wooden construction. As always, safety and legislative compliance is top priority, but one of the biggest challenges was how to improve reliability of plants, most of which were several decades old and required significant capital investment, while at the same time ensuring that they were economically viable. This required deep consideration of scope of work as well as disciplined execution.
Yes, the old plants certainly did provide a number of challenges to becoming as reliable as the newer, more advanced plants. However, very new plants, as we're about to discuss, can be equally challenging, albeit in different ways. Which moves us on to focus on one of the plants of your portfolio, a real-world example which would soon become your number one area of focus, at least as far as I was concerned.
Yeah, absolutely, Jeanne.
Yeah, so this new greenfield world-scale ammonia process plant is the one I mentioned earlier in the intro. As the company's largest investment, this project stretched the company's balance sheet and made us, as well as our investors, keen to see it run consistently and at nameplate capacity. It was built before either of us were actually in the company, but was executed under a lump sum turnkey contract. Now, every type of EPC contract has its strengths and drawbacks, with this type of contract being great for controlling cost and initial capital outlay, but at the cost of an inbuilt incentive for the contractor to cut corners, especially in areas that the owner might not notice, at least initially. So can you share with us your early experience with this plant and how you came to discover the operability challenges that arose from the decisions that were made during the design and construction phase of the project?
Yeah, the plant was operating at a reliability level of just over 60% in 2020, which was well below the target of 95, and this was obviously my number one area of focus. Unfortunately, there was not one specific bad actor leading to the poor reliability, but rather a host of challenges. A significant cause of downtime was the fact that the plant did not have its own dedicated boiler, but rather relied on a steam supply which serviced the whole industrial site. The problem was that the site-wide steam pressure was different to the operating steam pressure of the plant and was not available instantaneously. During process upset conditions, steam would need to be imported to keep processes operational, but the lower steam pressure exacerbated the upset conditions and more often than not resulted in a full plant trip. Considering the time to restart was 5 to 7 days, there was a significant financial impact. This is a prime example of how removal of scope items, in this case the dedicated boiler, to save cost, may seem viable during the planning stages, but results in significant unforeseen losses later. Another design decision which resulted in reduced reliability was driving most of the large rotating equipment with standard steam turbines and not installing backup electrical drives. Not only would this have allowed us to keep critical rotating equipment running during a steam upset or reliability failure of the turbine, but it would also have allowed us to conduct online preventative maintenance to further reduce failures. Spurious trips due to instrumentation failure were also a significant source of downtime. In many instances, there was a single point of failure, meaning that if a single probe failed, the plant would trip. The last source of significant downtime that I will mention is the numerous failures of dry gas seals on major rotating equipment. Again, there was a little redundancy built into the dry gas conditioning skids, which meant that the system could not be serviced as regularly as necessary. And when equipment repairs did need to be made, project phase decisions increased the downtime necessary. For instance, introducing more isolation points in the plant would have reduced the size of the section required to be de-inventoried before the repairs could be done, and would have reduced the overall amount of downtime for any given repair.
That's a lot of decisions made during the design stage, which were inconsistent with best practice. No dedicated boiler, no backup electric drives, no 2 out of 3 instrument redundancies, etc. And all of these decisions lowered the initial capital outlay, but at the significant cost later of downtime and unreliability, a false sense of economy. And as you are also well aware, Paul, we inherited a situation where the company had already settled with the contractor to absolve them of all future liability and responsibility for fixing these issues. So the burden of fixing the plant fell on you. And as we both knew, the first turnaround was key. But unfortunately, the COVID pandemic delayed this. Can you talk about how you went about eating the elephant?
Yeah. So, firstly and importantly, we kept an accurate record of all reliability events, including weak signals that could indicate a failure was imminent. We then ensured that a root cause analysis was conducted for each, resulting in a list of corrective actions. This allowed us to prioritize actions and execute them during any opportune outage, time allowing, of course, or for the turnaround. Unfortunately, most of the fixes had to be executed during the turnaround, but there were a few that we could do while the plant was operational or during opportune outages, such as improving lightning protection. We'd experienced a number of trips due to lightning strikes, which are preventable. We also installed an independent power supply to back up critical control systems while the plant was online. Preventative maintenance schedules were reviewed and optimized, but with the lack of redundant systems, many of these could only be executed during outages. So execution of most of these had to wait until the first turnaround.
Which of course led to a lot of work in that first turnaround when it finally did take place, and under the quite difficult pandemic conditions. Unfortunately, the restart after turnaround was also troubled. Can you share your thoughts about why that was and what we learned during this experience?
Yeah, so with the pandemic, several of the contract companies faced challenges with staffing, and QA/QC became a challenge, with several work packages having to be redone when attempting to restart the plant. With the turnaround being postponed and the high demand for turnaround contractors post-COVID, it could only be conducted in January, but then weather conditions are suboptimal. Louisiana experienced an uncharacteristic freeze, which resulted in damage to the tubes of a key heat exchanger. Unfortunately, the repair shop was inundated with customers in similar circumstances, which led to further delays. One of the major challenges experienced during the turnaround was the repair of the waste heat boiler, which contains approximately 3,000 tubes. As we were unable to repair all the cracks between the tube sheet and tubes, we had to fabricate a spare heat exchanger in the end.
Yes, that really did contain a lot of unexpected discoveries, which, in addition to an already large turnaround scope, was particularly troublesome. I think that's a good time to take a moment to hear from our sponsor, Pilko and Associates.
Pilko Associates is the leading advisor to officers and boards on operational, EHS and ESG risks and liabilities in the global chemical and energy industries. With 45 years of experience, the firm advises on driving rapid, dramatic and sustainable improvements in safety, reliability and competitiveness. Pilko's advisors have an average of 38 years of relevant professional experience in operational and executive roles with major energy and chemical companies. For more information, go to pilko.com.
So, we've discussed a number of operating issues that were created by the decisions made in the project phase of this particular plant, and how many of them were actually finally addressed during the turnaround. So, I'd like to go to the startup after the turnaround, and you began an intervention to drive operating excellence into the site, starting with leadership and culture. Can you share the steps you took to get this plant to become a reliable plant?
Yeah, so as mentioned before, people are key to running a safe, reliable plant. One of the first things I did was to change the structure. This resulted in an initial increase in headcount, but improved technical capability and capacity. Along with the new structure, accountabilities were clarified to ensure that everyone knew what they were expected to deliver, with nothing falling in the cracks. We also focused on changing the culture from a victim mentality to one where we all believed we were in charge of our own destiny. Training was a big focus area, both from a leadership as well as an operational perspective. Several of our young leaders had previously been in technical roles with no real guidance on how to lead a team of people. This was addressed through focused training programs. Mentorship programs were also set up for key individuals to accelerate their development. Operators were placed on schedules where they would spend significant time on the newly revamped training simulator, where they were taught in a low-pressure environment to quickly react efficiently to various plant upset conditions to avoid cascading into a plant trip. As far as possible, we also automated certain plant processes. thus reducing the probability of operator error occurring during these routine events. Ultimately, the engineering fixes and people focus resulted in the reliability of the plant improving from just over 60% in 2020 to 94% in 2023.
That was a real accomplishment for both you and the team. Well done. I'd like now to step back a bit and think about the broader lessons learned. And the concept I'd like to discuss further is what I've heard called value engineering on projects. Inevitably, as a project goes from the concept to detailed engineering, the cost continues to climb as you find out that things weren't anticipated and solving them requires more money and/or time. I'm not sure I've ever known a project that went down materially during this progression, but I can quote quite a few that doubled in price.
Yeah, my experience, Jeanne, is exactly the same.
But what still surprises me is that after all the years of experience, we as an industry still do value engineering on projects when we have so many examples of it costing more to fix it later in lost production. I first came across value engineering right after I earned my engineering degree, where in class I'd spent a lot of time learning techniques to improve energy efficiency, given the aftermath of the 1970s energy crisis. However, my first job designing a project had all my superiors encouraging me to strip out all the energy efficiency parts of the project to lower the initial cost outlay and to raise the IRR. And this might sound like a sound decision, but I always thought we were mixing apples and oranges. The base project always had a higher IRR, but was based on very cyclical earnings of a commoditized business. And the lower but consistent return on the energy efficiency projects were comparable when adjusted for risk, and proved invaluable when economic conditions were rough and lower operating costs kept you from being underwater financially.
Yeah, I agree. Projects need to consider the cycles when evaluating the economic returns. Companies need to survive when times are tough. Investors and CEOs generally don't want to break even or lose money in any particular year, even though the cycle may turn in future.
Yes, and I also inherited another example of value engineering when I was a new refinery manager with a project that had been installed to allow the refinery to run heavy Canadian crudes. And again, some of the key equipment upgrades had been value engineered out to ensure that the project could stay within its original budget. But to reliably run these heavy crudes, this equipment was absolutely needed, and we ended up installing it in the next turnaround. And of course, the incremental capital outlay always looks like a great investment. But the question is, shouldn't this have been included in the original project? I suspect this project would have still made sense financially, but it certainly brings to question proper decision-making on the project from the very start.
Yeah, absolutely. Something which I also think is worth mentioning is the reputational damage to the management team of not delivering on the original promise or delivering a project which is suboptimal and having to go back to investors to explain why additional capital is required to optimize the asset.
Absolutely. So, Paul, we've covered a lot of ground in this podcast. Any last words of advice for people involved in large projects, whether they be in the design, construction, or operating phase?
Yes, Jeanne. So during the design phase, consider what investment will realistically be required over the life of the asset to ensure that it operates efficiently. If many obvious improvements are identified soon after startup, we either cut too deep during the value engineering phase or did not spend enough time developing the scope. Ask yourself the question, what will the future management team say about our project in 5 years' time? The quality of the work should take priority over the schedule. There's no benefit in completing a project on time if there's a lot of rework later. Overall, this takes longer and costs more. During the design and construction phases, ensure that those who will be operating the plant provide input. At the end of the day, they will be under pressure to ensure that the asset performs and need to take full ownership. This viewpoint will help balance the focus on initial cost and schedule. And lastly, do not underestimate the impact of the quality and preparedness that the plant employees will have on the operation of the facility.
That's a great way to conclude our podcast today. I want to thank you, Paul, for your time, and more importantly, for sharing your experience in operating projects safely and reliably in a high-hazard industry.
Thank you for having me here today, Jeanne. It's been my absolute pleasure talking with you.
Thank you, Paul. And until next time, stay safe.